Welcome back, Algebra 2ers. Congrats on making it to Chapter 5. Now dealing with polynomials and how they're graphed, how they look. A bit of vocab that's given to you, dealing with some terms that you've already seen, monomial, polynomial. This just means that you're dealing with more than 2 or 3 terms, so lots of terms. And behavior, we'll talk about how these polynomials are graphed as they continue to the left and to the right. We'll see the degrees. We'll see that what the standard form looks like. We'll see turning points and go from there. If you want to read through this stuff, you can. It goes over some basic vocab for monomial, saying what that encompasses, talks about the degree, and says that it is the greatest thing or greatest degree of the first polynomial. So the highest polynomial is really big here, or the highest degree of the first term in the polynomial. We get a general identification for what a polynomial looks like, saying how it's standard if it can go in descending order for the exponent. So this is the general way that they write this. And from this example, we see a bit picked apart. We see that if we have a variable being cubed, that's cubic. If it's squared, that's quadratic. Linear, it's just constant with a variable of x, and then just a constant on its own. This table might be helpful to hold on to if you're still trying to get used to some of these terms. The first example has you just going and rewriting polynomials so that they're in standard form, classifying also the polynomial's degree. So we see a little bit of a jumbled bit here at first, but if we rewrite this, the highest exponent is 3, so that needs to go first. We can also start to combine our x terms of negative 3x and 7x. We can then rewrite negative 3 at the end. This is cubic based off of the exponent of 3. These aren't too bad. Really just getting you familiar with what these look like if they're in standard form. We're then introduced to the idea of turning points and end behavior, where the end behavior says or dictates where exactly the graph's heading, to the far left or to the far right. Some examples are sketched out here. When this goes up and up, or down and down, down and up. We've actually graphed parabolas that looks like this, so this should look familiar. The up and up portion should also look familiar, minus this turning point right here. So we'll be using a lot of terms of up and down, and to the left and to the right. And what's cool is that we can dictate what all of this is going to look like, even if we only get a small glimpse seen here. And we can dictate what that looks like based off of the end behavior, dealing with the polynomial's leading term. So what does this say? This says that if we have a coefficient for our leading term that's positive, and it's an even degree of n, so this could be 2, 4, 6, 8, this is implying that this is going to go up and up, as seen here with this visual. Whereas if we have the positive coefficient but the exponent's odd, this is going to go down and then up, just like this. If we have a negative coefficient but an even exponent, we're going down and down. If we have a negative coefficient and an odd exponent, this is going up and then down. So you can use these visuals and use this table as we move forward. So this question's asking us what the end behavior is. Again, this is all based off of the very first leading term. We know that this is already in standard form, this 3x to the 4th minus 2x to the 3rd plus x minus 1. So since we're already in standard form, all we really need to do is just nitpick this one. So we know that a is positive, meaning the 3 is positive, 3. We know that 4 is our exponent, and that's even. So if we look at the table, we're looking for where a is positive, n is even. We can say that this is going to go up and up. So it should look something like this. Take this time now, pause, try the next one. But since we're dealing with a negative a term and our exponent is odd, we're looking for where this correlates. So a is negative, our exponent's odd, so this is going up and down. So it's going up to the left, but it's going down and to the right. So it should look something like that. We also are introduced to the idea of turning points because some of these are not just going to be given quadratics or parabolas. So we sometimes need to keep in mind that these can go a little crazy. They could go down, they could swing up, and then go back down again. And this would still retain the up, then down function or motion. So how this works with the turning points, we can dictate that the graph of the polynomial function, assuming the degree is greater than or equal to 1, has at most n minus 1 turning points. The graph of the polynomial function of odd degree has an even number of turning points. The graph of a polynomial function of even degree has an odd number of turning points. The next visual gives us a little bit more light as far as how these work. Take this time now, maybe pause, get a feel for them. As far as describing what's going to happen with these, we're talking about, well, the very first, again, leading term. So if we rewrite this to negative 2x cubed plus x plus 3, we know that our leading term is going to be 3 for the exponent. So just based off of the visual, we know that this would be rising to the left, but going down. We know that since this is degree 3, there are going to be 0 or 2 turning points. So that's what we know. So this has either 0 or 2 turns. We'll soon be able to dictate exactly how many there are. For the next one, this is negative x cubed. And if we take a look at this, this is adding 3x. Leading term is negative x cubed, so this is going to be going down and to the right, but also up and to the left. So this is also either 0 or 2. We can also talk about the next piece here. This is already in standard form, negative 8x cubed plus 2x squared minus x minus 2. We know that this is going to be going down and to the right. And this is going to have at the most 2 turns. So it's either 0 or 2 turns. So it could look like this with 0 turns. Or as it goes down, it might swing up and then go back down again. So it could be a mix of those. Based off of this, again, there's really not too much that's wordy here. A lot of this you could just think out on your own. In reality, this one actually has 0 turning points, I think, so that's a good rule of thumb. We see in the next few examples, we can start to see if a term is going to be linear, cubic, quadratic, or quartic, just based off of if the differences are constant. We see if the first differences are constant, then it's linear. We see if the second differences are constant, then the function is quadratic. Third differences are constant, then it's cubic, and so on. So a lot of this is just going to be looking at these tables seen here and nitpicking what the difference is. So from negative 13 to negative 4, that's a change of negative 9. This is going to be 3. This is 3. This is 9. Of course, plus 9. We also see plus 21. And then jumping to here, this is going to be adding on 39. Pretty sure. If we check the arithmetic here, 9 to 3 would have to subtract 6. 3 to 3 would be 0. So measuring differences here. This would be 6. This would be a change of 9 to 21, so this would be 12. 21 to 39, this would be a change of 18. We then see the change here of plus 6, plus 6, plus 6, and plus 6. So this was the first difference, the second, and the third. So since this is the third difference, we would say that this is cubic. So this could be some term like x cubed and whatever else comes after that.